Okay, today we're going to be talking about systems of linear equations, but only two variables and two equations. Okay, next time we'll talk about three variables and three equations. And you remember this from Algebra 1. This was when we did substitution or elimination. Okay, it's going to be just the same, except it'll probably seem easier. Okay, so a system of linear equations is going to be more than one equation with two variables. I'll get her later. Okay, so a system of linear equations is something like, something where we have two equations like 2x plus 3y equals 4 and x minus y equals 0 or something, And basically there's three different ways that this can go if we have two variables and two equations. Okay. We could have a line and another line, and then this would be the solution. This would be the value of x and y that makes both equations true at the same time. So that would be one solution. We could have something where we've seen in this class that, a given line can have different equations and it's still the same line. We could have a line and then, just another name for the same line. So two at once. And really we're looking for where they intersect. That's the geometric representation of the solution of a system of linear equations, is the intersection. And if that's the case, then we have infinitely many solutions here because it's the same line. It overlapped everywhere. So I would just, these are all solutions, but then I could say that's another one, and you could just go as, as close as you like. Infinitely many solutions. And then there's the case where there's no solution. What kind of lines would not have a solution, not have some kind of intersection? Parallel lines, yeah. So I'm going to try to draw parallel lines here. Okay, if these lines are parallel, then they never cross. That's kind of probably the definition of parallel that you took in geometry. And so we say that there is no solution. But we're not going to solve by graphing in this course. That's just a really inefficient way to solve a system of linear equations. Okay. So what we're going to do is we're going to use substitution and elimination. Okay, for substitution, the first step is going to be solve for one of the variables. And then after we've solved for one of the variables, we'll use that and plug it into the other equation and take it down to a one variable equation, which is basically what we spent the entire first unit studying. Now for elimination, I haven't started with number 2, but we're going to eliminate one of the variables by either adding or subtracting equations from each other. So add or subtract. Okay, then we'll solve for that one variable, and we'll plug in on one of the original equations to find the second one. Okay, so I'll come back with more steps, maybe at the end, once we have a better idea of what we're actually doing here. So I think the best way to proceed is to just do some substitution. Okay, so let's just start with this one. Y is equal to negative 3x minus 5. Now this one is, you look at it and you see this one is just prime for substitution. If you remember from Algebra 1, right? If there's one that's just staring you in the face and it's like, you need to use substitution for this, well, I think that's the best way to go. In general, if they're both in standard form, I'm of the opinion that elimination is generally the way to go, but that's just my preference. They both work. It can be proven that they're equivalent. Okay, and in a linear algebra class, that would be something you would see. But that's something that we're not going to include here. So, knowing that y is equal to negative 3x minus 5, I'm just going to rewrite the second equation, but replace y with negative 3x minus 5. And then I'm going to distribute the 3 and rewrite the equation again. 5x, 3 times negative 3x is negative 9x. 3 times negative 5 is negative 15. I'm going to collect like terms. 5x minus 9x is negative 4x. Add 15 to both sides. Negative 4x equals 16. Divide by 4. X equals negative 4. Now that I've got x, I'm going to go back to one of the original equations that's printed on the sheet of paper to get y. Okay? If for some reason, you've copied something down wrong, or you go to one of your equations, you could potentially get, a wrong second value. Okay, so I'm going to go back here. I've got an equation for y explicitly in terms of x, so I'm definitely going to use that. Okay, so I'm going to go over here, and I'm going to say, well, y equals negative 3x minus 5, and x is equal to negative 4, so I'll say y is negative 3 times negative 4 minus 5 more. So negative 3 times negative 4 is positive 12. And 12 minus 5 is 7, so I've got y equals 7. So if I were to graph these, they would intersect at the point negative 4, 7, which is in the second quadrant. Okay, so the solution, you could write it like this. I'd be happy with that. You could also write it as negative 4, 7, write it as an ordered pair. That would be great too. It's pretty much what we're looking at. And for our second example, let's do one where we substitute on x. So x is equal to 2/3 of y, not 2 divided by 3y. Okay, so something like that. And 3x minus y equals negative 3. So I'm going to freeze it. I'll solve it with substitution. I'll walk around and see if it's going well for you. If it's not, I can help. But I think y'all know what to do. we generally seeing -2 and -3 as our answer? Yes? No? -3, -2. Is it? Yeah, you got -3 and -2, but y is -3 and x is -2. Remember the x is going to come before the y, right? So you got the same answers, and so that's like the one way that you could potentially get tricked, right? Is if you solve for y first, and you went to write it down as an ordered pair, and you're like, oh, I want to solve for that one first, so I'll just write it first. That would not be the same, right? So when we write the ordered pair, it's implicit that the first coordinate is the x value, and that the second coordinate is the y value. And since like I said before, if you have it in standard form, like ax plus by equals c for both equations, it's oftentimes going to be the case that the way to go is elimination. Okay, this one is just prime for elimination. Anybody see like what makes this one prime for elimination? Yeah, we've got the x on top, and right below it we have -x. So what we can do is we can add the two equations together. Okay, and what we're really doing, I'll write it off to the side, is if it's the case that we have -x plus 2y equals 14, and x plus y is equal to -5, well then I could add x plus 5 to x plus y to one side, and -5 to the other. And since, these two things that I've put parentheses around are the same thing, I haven't changed the equation because I've added the same thing to both sides. So that's why it's valid for us to add two equations together or subtract two equations from one another. So what I'm going to do is I'm going to add the two equations together. And then you add down. X plus -x is 0. Y plus 2y is 3y. And then 14 minus 5 is 9. Divide both sides by 3, and I'll get y is equal to 3. Then you want to go back to one of your original equations. And this will become more of an issue next time when we do 3x3 systems, that you want to go back to one of your original equations. And so I'm going to say x plus y equaling -5. Y is equal to 3, so I'm going to do x plus 3 equals -5. I'll subtract 3 from both sides, and I'll have x equals -8. So my solution is x is -8, and y is 3. Okay, here we have another system where both lines are represented in standard form. And so I'm thinking it'll probably be one I want to use elimination on. But I don't have any variables that are just, perfectly lined up to just add them together or subtract one from the other. So what I'm going to do is I see this 3 here, and I want it to be 6, so I could add it to the -6 and then make the x's be eliminated. So what I'm going to do is I'm going to multiply both sides of the equation by 2. Right, if 3x plus y is equal to 1, then we could double both of those things, and they'd still be equal. So I'm going to say that 6x plus 2y is equal to 2. And now I'm ready to do the elimination. Okay, so I'm adding these together. I'm getting 6x plus -6x is 0. Plus 2y minus 2y is also 0. Okay, I add 2 plus -4, and I get -2. So to this equation I've got, after I've eliminated, and looks like I've eliminated both of the variables, is 0 plus 0 equals -2. And you think about what values of x and y make that equation true. No values of x and y could make that equation true, because 0 plus 0 is never going to equal -2. Mainly because 0 plus 0 is always going to equal 0. Okay. So when I see something that's patently false like that, I'm going to say that the system has no solution. Okay, if you wanted to write it as the set of solutions, it would be the empty set. Okay, and here we have another one that's pretty much set up for elimination. Right? The numbers don't line up perfectly, but if I was to take the top equation and multiply it by 3, it would be pretty set for elimination. Okay, so I'm going to multiply equation 1 by 3. And so I'll have 3x minus 15y equals negative 9. Okay, now I'm going to add the two equations together. And I'll have 3x minus 3x is 0. Negative 15y plus 15y is 0. And then I've got negative 9 plus 9 is 0. Okay, now I've got some kind of equation like 0 plus 0 equals 0. And you think to yourself, what values of x and y would make that equation true? All of them. Yeah. So just as long as they satisfied each of the two equations. And now we said earlier that that's when the lines were coincident or the same line. So it's all of the x's and y's. But it's not just any old x and y. You probably can't let x equals 0 and y equals 0, because then you would be saying in the first equation x minus 5y would be 0 minus 5 times 0 is negative 3. So 0, 0 doesn't work. But there are infinitely many solutions. And like I said up above, this is because this is really two names for the same line. Okay, so I'm going to just, kind of show you what that is. So if I have x minus 5y equals negative 3, well, I could solve for y, and so I'm going to say negative 5y is equal to negative x minus 3, and then divide everything by 5. I'd say that y is equal to, negative 1 divided by negative 5 is 1/5 of x plus 3/5. And then if I took negative 3x plus 15y equals 9 and solved for y, I'd have 15y is equal to 3x plus 9. And then I divide everything by 15, and I get y is equal to 3/15 of x. Well, 3/15, that's the same number as 1/5. And then 9 divided by 15, well, I guess if we divided 9 and 15 both by 3, we'd get 3/5. Okay, so we can see that they're the same line. And just the last thing that I have to say about this is that if there's infinitely many solutions in the 2 by 2 case, it will be because one of the equations is the exact same as the other multiplied by some number. Right? So basically notice that the second equation is equal to 3 times, well, I guess it would be negative 3 times the first equation. And that will always be the case with systems that have infinitely many solutions in the 2 by 2 case. Okay, here we've got a word problem that's going to probably turn into a system of 2 linear equations. The sum of one number and 3 times another is negative 12. Okay, let's turn that into an equation. The sum of, so that's where we're going to add two things together, one number's x, and 3 times another number, we'll just call that other number y, is equals negative 12. The difference of twice the first number and the second number is 32. What are the numbers? Here we have a system of 2 equations and 2 variables. And looking at the equations themselves, it seems like elimination might be the way to go. So what I'm going to do is I'm going to take the first equation and I'm going to multiply it by negative 2. So I'll have negative 2x minus 6y equals, okay, if I multiply negative 12 by negative 2, I'll get positive 24. Okay. Now I'm ready to add these two equations together. And I'm going to get 2x minus 2x is 0. Negative y minus 6 more y will be negative 7y. And I add 32 to 24 and I'll get 56. Dividing by negative 7, I'll get y is equal to 56 divided by negative 7 is negative 8. Then I'm going to go back to one of my original equations. It doesn't matter which one you choose, right? Because if they're both true, then it shouldn't matter. Okay, I'll just choose the first one because it's got x. Just don't have to divide by 2. So I'll say x plus 3y equals negative 12. I'll substitute on y. And so x minus 24 equals negative 12. I'll add 24 to both sides, and I'll get x equals 12. Okay, so the two numbers are 12 and negative 8. Okay, another one. At a baseball game, Annie bought her family 4 hot dogs and 3 large Cokes for $22.25. First, I'm going to define my variables. I'm going to let x be the number of hot dogs. Well, no, I guess it'll be the price of a hot dog, right? Because I already know the number of hot dogs. So x is the price of a hot dog. And y will be the price of a large Coke. So the Annie equation is going to be 4x plus 3y equals $22.25. Dave bought his family 5 hot dogs and 4 large Cokes and paid $28.50. How much does a hot dog and a Coke cost? Looking at it, I can see that it's not really ideal for elimination. Really at all. So I think what I'm going to do is I'm going to multiply both equations by some number to just get x ready to be eliminated. So I'm going to start. One technique that will always work is if we have, here we have 4x and here we have 5y. I'm going to multiply the first equation by 5 and the second equation by 4. Okay? Because if we do that, we'll end up with 20 x's on both equations. Okay, so over here, this is turning into 20x plus 15y equals, and now this is looking like a job for the calculator. Somebody do that for me. $22.25 multiplied by 5. Okay, what was your question again?
Like, I was asking since you're looking at it, does it want to be negative?
We can subtract one equation from another as well, and that was my plan on this one. But if you wanted, you could multiply the bottom one by negative 4. Okay, so the question was, we wouldn't have it prime for elimination. We wouldn't have 20x and negative 20x. And if you prefer to just add the two equations together, what you would want to do is multiply this one by negative 4. Since I haven't subtracted one equation from another yet, I think I'm going to do it this way in this example, but you will get the same answer. It doesn't matter. Okay, so multiplying this one by 4, I'm going to get 20x plus 16y equals, what was that? $114, thank you. And then I'm going to kind of focus on this equation, this system of equations in blue, which is equivalent. It will have the same solution. And I'm going to subtract this equation from the top one. Okay, so I've got 20x minus 20x, that's 0. 15y minus 16y is negative 1y. And $111.25 minus $114 will be negative $2.75. All right, meaning that y is equal to $2.75. Okay. Now we need to go back to one of the original equations to find the value of x. So I'll just choose the top one. You can choose the bottom one. You get the same thing. 4x plus 3 multiplied by $2.75 is $22.25. All right. All right, this is another one that's probably going to need a little bit of calculation. See up in the front, punching in those numbers. What was that? 3 times 275?
825.
825, that does sound reasonable. I just would hate to try to do that mental arithmetic and do it wrong and be completely wrong in the example. That would be bad. So $8.25. That was $22.25. All right, so I'm going to subtract the $8.25 from both sides, and I'll get 4x equals $14. Okay. And then x is going to be 14 divided by 4, would be half of 7 is $3.50. Okay. Now, if you look back at the question, it asked for the price of a hot dog and a Coke. Maybe you're just one person going to the baseball game and you're thinking, I just want one hot dog and one Coke. So that means that x plus y is equal to $2.75 plus $3.50, and maybe in a place without sales tax like Oregon has no sales tax, that would be $6.25.